Welcome, good morning. We're kicking off today with Geoscience Grab Bag number 4. And with us today we have Stiassny from the University of Colorado at Boulder. We have Patrick Stowell from the University of Sheffield, Melanie Stiassny from the American Museum of Natural History, and James Watson from Oregon State University. And I'm going to turn it over to Lee to get us started.
Hi everyone, good morning. My name is Stiassny and I'm from the University of Colorado in Boulder. And I'd like to share some important new experimental results on the interaction of rover wheels with lunar and asteroid dust. So this work is done in collaboration with the NASA Ames Research Center and the University of Central Florida. Yeah, let's get started. So result number 1 that I'd like to share with you is that we measured the dust grains charged to hundreds of volts due basically to human activities. Secondly, and this might be a little bit intuitive, different types of dust are going to charge differently. So what does this mean when we are thinking about having long-term habitats on the surface of the moon? As you might all know, there's this new Artemis program that plans for the eventual return of humans to the surface of the moon. So, firstly, dust is a human health hazard. When astronauts breathe it in, it could harm their health, and so this becomes especially crucial when dust manages to get itself tracked indoors or into the spacesuits themselves. Secondly, dust can easily clog mechanical joints, and they can obscure sensors, including solar panels. This is something else to note. Thirdly, if the dust is charged, then it can go on to cling to equipment and pose the risk of electrostatic discharge. So all these things about dust should help to inform our design of equipment and habitat moving forward as we go back to the moon. Oh, and I've included here a little picture of the astronaut Harrison Smith, and you can see that his spacesuit is entirely clogged up with dust, basically from the boot up to his chest. So, what is the process by which rover wheels charge the dust? If you have ever rubbed a balloon against your hair or taken a sweater off in the middle of winter on a cold, dry day and felt that spark of electrical discharge, congratulations, you have experienced triboelectric charging. And what is it? It's a really simple, familiar concept. When two materials rub against each other, they will transfer charge between them. And the amount of charge that's being transferred depends on the type of materials, the amount of rubbing, how vigorous, how long you do that rubbing, as well as the specific surface properties of the two objects that are being rubbed together. So if you think about it, this can definitely occur when spacesuit boots rub against the dust on the surface of the moon, and it can also happen when wheels rub against this dust. So, how significant is this charging? Well, as scientists, we definitely want to measure this, and we came up with a pretty simple and straightforward experiment to test this out. And what we wanted to do is measure the charges on the dust that's been kicked up by a rover wheel. We measured this for 2 kinds of dust, lunar and asteroid. So this is just a simple schematic of what we did. We have a rover wheel, we placed it on a bit of dust, and as it's turning, it's going to kick up the dust into our charge detector. And that's a little picture of the rover that we used for our experiment on the dust bed at the NASA Ames facility. So here's a cute little video of our little rover wheel in action as it kicks the dust into our detector. And that's it. So I want to give you 3 main points to take home from our experimental results. On the right here is a graph showing the charge distributions for both lunar dust and asteroid dust. And right off the bat, you can see that both of them have overwhelmingly positive charge. The second point is that, well, clearly there are different charge distributions for different kinds of dust. And you can see that the asteroid dust can charge up to significantly higher than the lunar dust. And the third point is that if you do the conversions, you'll find that in extreme cases, individual grains of dust can charge to hundreds of volts. And these dust grains are on the order of like 20 microns. So how can we use this knowledge to plan future rover-based missions? Well, we know now that the charging of the dust really depends on the type of dust that the rover is traveling on, but it can also depend on a few other factors that we should probably be careful about. For instance, we know that in the absence of sunlight, we expect the dust to stay charged longer. So if we were to set up a lunar base in a permanently shadowed region of the moon, there's going to be no sunlight or plasma to help to dissipate this charge. And so the risk of electrostatic discharge will be that much higher. Keep in mind that permanently shadowed regions is where we expect to find water on the surface of the moon. So those are significant regions of interest. Secondly, there is a theoretical paper that predicts that the faster a wheel is turning, the more charge will be transferred between the wheels and the dust. So we might have to think about recommending a maximum safe speed when the dust is traveling, when the rover is traveling on the surface of the moon, depending on the equipment around it and its tolerance. Finally, if you think about it, when the wheels are charging the dust, simultaneously the dust is also charging the wheels, exactly the same amount of charge, but in the opposite polarity. So this is something to be careful of as well. And I leave you with a little thought on moving forward. Thank you.
Okay, so I'm Patrick Stowell from the University of Sheffield, and we're going somewhere equally as dark, I guess, but at least there's oxygen here. So in the UK, we have quite a densely packed rail network. A lot of that network was actually built in the 1900s, and it's still in use today, which means it needs to be continuously monitored and maintained to actually ensure that it's safe for currently operations. Now, one problem that UK rail managers currently face is in railway tunnels, there have been cases of hidden voids opening up. So basically, these are voids that are left over actually from the construction of the tunnels themselves, or voids that have formed over time. And these can actually degrade, and then actually material can fall down the shaft here, and it has the potential to actually collapse onto the track. Now, this is a problem because you can't see these from the rail bed, and the only method currently in use to find these is through invasive drilling campaigns, which is literally drilling through the roof of the tunnel and seeing if you punch through to a hole on the other side. So we've proven at the University of Sheffield recently that it's possible to use an alternative technique, cosmic ray muon tomography, to image these voids in an extremely short space of time, on the order of a few hours, completely non-invasively. So just as a very quick introduction to cosmic ray tomography, anyone who's familiar with getting any sort of X-ray done, the technique works by using the absorption of cosmic ray muons as they pass through a material to image the internal density of that object. Now, muons are basically just heavier, more highly penetrating versions of electrons, which means they're ideal for cases when you want to image large objects like volcanoes, tunnels, and things like this. But the one caveat with this technique is it relies on using naturally occurring background radiation, which means if you want to actually form an image with high granularity, high resolution image, you need to run for a really long period of time, on the order of months, to actually collect enough muons to form an image. Now that's a problem because on the UK railways, possessions are currently taken overnight where maintenance work takes place. And these possessions are on the order of a few hours. For this technique to be applicable in any scenario where you're time constrained, you need to find a way to produce actionable information with a significantly less number of muons. So we've recently demonstrated that it's basically possible to do this by flipping the problem on its head and saying, let's not have one detector placed somewhere outside of the tunnel and produce one really high granularity image and see what's in it. Instead, we know what we're looking for. We know we're looking for a hole in the rock above the tunnel. So instead, let's take a coarse resolution detector, run it for shorter periods of time, but run it at lots of different points. So we're essentially taking a scan along the tunnel as we drive through. And what this allows us to do is we can put our detector at various points, and there is a good chance that one of these points is going to be below the actual problem area, which means that we can actually identify regions where there's an excess in the total muons that we see in a much shorter period of time, on the order of half an hour or so. And we've taken that one step further and asked ourselves, well, what is the minimum amount of information that you actually need to do this? And it turns out that even if all you do is measure the total number of muons, you don't have any granularity in your detector, you're just counting a single rate, even then, as you step through the tunnel, you'll see this increase in the total number of muons when you get to problematic areas, and that itself is enough. It's not enough to produce a nice image that you can post on Instagram or something like this, but it is enough to tell you if there's a massive gaping hole in the rock above you. So it can tell you where you have the biggest issues. So we recently demonstrated this. We chose a disused railway tunnel near us in the UK, and our partners, civil engineering partners, Central Alliance, took us in, and we did this scan of just measuring the total muon rate as we drive through the tunnel. And you can see it drops off, and then as we get further and further into the tunnel, there are these variations here, which give basically a signature of what the rock above us in the tunnel is actually doing, what the variation in the ground is like. Now, this tunnel was specifically chosen because it has 3 open ventilation shafts, and these show up as these clear spikes here. So in this trial, we can definitely see open shafts, which we hope to do. If we couldn't see those, it would be a huge issue. But the nice thing that came out of this first field trial is actually we identified an additional region here, which shows up, which we can't explain by any variation in the rock above the tunnel, by varying, buildings or anything like this. Now, if we actually zoom in on this area here at 80 meters, you can see that there is an excess compared to what we expect, which is quite wide, right? It's over several meters, and it's actually a lot wider than the cases where we have open shafts, which suggests that already this is a hidden void, which has started to degrade and widen over time, and potentially materials already start to fall onto the lining of the tunnel itself. Now, what we weren't told when we actually went into this is this shaft here had already been cored by our civil engineering partners, and they just decided not to tell us about it as a kind of a curveball for us. So this is the first completely blind test of proving that this technique works to find hidden voiding in railway tunnels. And it demonstrates that not only is muon tomography a powerful technique for locating this sort of voiding, but also that this sort of standard long exposure limitation that comes up with the technique can be overcome if you're in scenarios where you actually know specifically what you're looking for, because you can flip it on its head and say, let's just record the minimum amount of information we can in a shorter period of time that will still give us actionable information.
Hi, everyone. Let me try and work this out. Yeah. Okay, so now for something completely different. I'm going to talk very briefly about some of the work I've been doing in a truly extraordinary place. And that extraordinary place is the Lower Congo River. So let me quickly introduce that place to you. The Lower Congo is the final 200-mile stretch of the Congo River as it flows to the Atlantic Ocean. And it does this after draining some 3.7 million square kilometers of Central Africa. That's more than a third the size of the continental United States. But the Lower Congo represents only 2% of that basin area. Yet it's home to more than 300 species of fishes. And just to give you a little comparison, the Mississippi River, which is over 2,300 miles long, is home to 150 species of fish. So the Lower Congo really is truly a hotspot of biological diversity on the planet. At the start of the Lower Congo River, huge volumes of water plunge down a narrow channel, and the water flows out at an average rate of about 46,000 cubic meters a second. That's about 2 to 3 times the outflow of the Mississippi into the Gulf of Mexico. So all of that water flows down this narrow channel, and it does it while dropping 90 feet in elevation. And the result is a whole series of these rapids. And I'm just going to show you a little video of one of these rapids, if I can make it go, sorry. Sorry.
Tripp and Scott crash head first into waves the size.
Thank you. So you get a sense of it, and you're going to see some crazy kayakers in that water. And those kayakers are actually taking measurements for us as they crazily go through that rapid. Anyway, so there's a whole series of these rapids down the length of the Lower Congo. And some of these are truly incredible, spectacular. And they together represent the largest stretch of white water on our planet. Okay, so we've mapped the location of these rapids along the Lower Congo River. And by genetically sampling populations of fishes above some of these rapids, below the rapids, from side to side in the channel, we've been able to show that these rapids really do form barriers. And they form barriers to fish swimming in water. Fish can't swim in these rapids. And they're very effectively dividing up populations and stopping them from interbreeding. But perhaps more importantly, they're doing this at an incredibly fine geographical scale. Okay, so the presence of these rapids definitely gives us a window into speciation in action. And it gives us some clues as to why there are so many fish in the Lower Congo River. But there's more, because in many places we were finding differentiation of populations where there were no rapids. So clearly something else was going on. And in one place, we found this particularly weird fish. Now, it's a blind, depigmented cichlid fish. It looks very much like a cave fish, but there are no caves. It's in the river. But what's the weirdest thing about this fish is that we only ever find it dead or dying at the water surface. Now, at one time when I was in this area, we got one that was alive, and as it died in my hand, bubbles formed under its skin and over its gills. This animal was suffering from catastrophic decompression syndrome. Now, up until this point, we've been thinking only about the rapids, which are very shallow water phenomena. Finding this fish dying in my hand of catastrophic decompression syndrome asked the question, could there be deep water here? And that was actually a very long story as to how we got at that question. But we basically used two methods. One was we used the pleiotropic effect of a Y chromosome on some young men, crazy whitewater kayakers. And we tricked out their kayaks with echo sounders, and we pushed them in the water, and down they went. So they give us a depth trace. And then we deployed this instrument, an acoustic Doppler current profiler, which really measures the velocity and direction of current through the water column. So we really get an idea what the water looks like if you're actually a fish. Okay, and the results that we got were quite astounding. So first of all, here's some results from the ADCP. It's deep. It's very deep. In places, in this particular case, it's over 525 feet deep. Now, that's the deepest place ever recorded anywhere in a river on the planet. So there is extreme depth there. But then look at the water currents. You're looking at the blues and the greens are going down, and the reds and the oranges and the yellows are going straight up. And so you have these huge cycling currents. And the red there you see are jets of water that are rapidly going up to the top. And you can imagine if you're a little fish living in the bottom there, you get entrapped in one of those red jets, it pulls you up to the top, you die of decompression, the fish's equivalent of the bends, on the way up. So we think we kind of explained why we find those populations of dead fish. But if you look a little bit further up, this is in another region of the Lower Congo, where it's not that deep, and well, it's still very deep, it's 295 feet deep, but just look at the currents. In this case, you're looking at streamwise currents. So the blues and the greens are going directly flowing away from you, the reds and the yellows are flowing directly towards you. And you can see that the two banks on either side, they're completely separated by a sheer zone of water flow. So water is separating the fishes that live on populations on either side of the two banks. So it's water everywhere, but really fish can't swim in it. Okay, so it really looks like the Lower Congo really is an extraordinarily unusual system, and it looks as if the water itself is dividing up the environment for the fishes. But there is still more. Remember the crazy kayakers? This is the purple is a trace of depth, and some of those depths are truly incredible. So they're recording depths of well over 700 feet in depth in certain places. So it really is an extraordinary system. But there is even more, because you remember this fish I told you about? So the river itself is clearly dividing populations up. Populations can diverge over time, and you can see how the water is actually forcing speciation in this system. So you can see why there's a lot of fish there. But some of them are really extraordinary. You remember that one. But we have all of these. Now, all of these fishes come from completely different families. They're only found in the Lower Congo River. This is probably the most extreme example of evolutionary convergence that you're ever going to find anywhere on the planet. So this really extreme system is not only giving us insights into how species arise in aquatic systems, it's also throwing up some really, really cool ways in which we can investigate how convergent evolution, one of the big themes of evolutionary biology, how that actually occurs. So it really is a model system. I've probably gone on too long, so our work is focusing on this particular system at the moment, so stay tuned. In a short while, we'll have quite a lot to say about the genes that underpin this system, as well as the morphological response to this extreme environment. So I'm going to stop there, just summarize my main points, which I've probably belabored too long, and they're up there so you can read them. And thank you for your attention, and happy to take any questions. I'm sorry it was so rushed. Thank you.
Give me 1 second.
Are you going to put that up on the big screen?
Yeah, use the frozen.
Forward, back. That's correct. Okay, thank you. Sorry to be the only guy that uses a PDF. And thank you, that's amazing work. I've enjoyed listening to all of you. Thank you all for coming and being available to listen to the work that I've been doing at Oregon State. So predicting illegal activities at sea. So illegal activities are bad in general, yeah. And if you go down to the coast and you look out to the sea, what happens over the horizon might surprise you, right? Maybe not here off the US coast, but in certain places, many places around the world, there are terrible things. Human trafficking, slavery, arms trafficking, narcotics trafficking, illegal fishing. And we want to be able to improve our ability to detect and even predict the occurrence of these bad events to deter them and find the culprits. The challenge is that the bad actors that commit these crimes it's in some ways invisible. You could see them if you have line of sight, but if you don't, you can't really see them. They don't transmit their GPS locations, in contrast to most legally operating vehicles. So the challenge is, how do we see what is invisible? What we've done is to use models of collective behavior to inform our approach. And the take-home message is that we've developed a technique that can actually predict, not just detect, but predict illegal activities happening at sea from the anomalous spatial behaviors of vessels that we can observe. So I'm showing you here a picture of starlings flocking, or more specifically, it's called a murmuration. I don't know if you've seen these movies of these beautiful things. you have these blobs, these amazing swirling blobs of starlings moving, fusing and forming blobs moving in and out. And they often do this in response to a predator, like a hawk, moving through the flock. And the challenge is very similar in this respect. What if you can't see the hawk, but you can see the starlings moving as they respond to the hawk? Could you infer the location of the hawk from the locations of the starlings alone? And that's what we've done for detecting illegal activities at sea from the locations, the anomalous spatial response of vessels that we can see. The data that we use are automatic identification system data, so that's AIS. This has really revolutionized the way in which we study how humans use and operate in the sea. So in the last couple of years, 3-4 years, the location of the majority of the world's vessels through time have been made available through certain providers. We've been working with Global Fishing Watch to do so. That data allowed us to do the following. So for one particular place, the Patagonia Shelf is one of the world's most productive fisheries regions on the planet. We get that data and we have a look at it. So I'm showing you here on your right the red dots. These are locations of all the vessels in that area. And I've done one very simple thing. I've identified who's closest to each other and I've drawn a line between them. This is the most basic form of geospatial analysis, is to identify your nearest neighbor and your distance to that nearest neighbor. It's very simple, but it's very powerful. It allows us to essentially characterize the shape of the system, how it looks. We do that by looking at the distribution of these nearest neighbor distances, as I've shown here. What's cool about this is that nearest neighbor distribution characterizes the system at that given time, and as time goes on, as the system evolves and say an illegal fishing boat comes in, the nearest neighbor distribution changes as the shape of the system changes itself. We can use metrics from information theory to quantify essentially how weird the system looks based upon changes in the nearest neighbor distribution. And to cut a long story short, this weirdness index picks up when illegal activities occur in this region. So here's a time series of this weirdness index over March 2016. The red dotted line, vertical dotted line, is on March 15th. That's my birthday, if anyone wanted to know. This is when this vessel, a Chinese fishing vessel, was found to be fishing illegally by the Argentine Navy. And they were subsequently chased and actually blown up by the Argentine Navy with sailors on board. This was in 2016, and it's happened, these kinds of activities have happened again since then. But what you're clearly seeing is our weirdness index is picking this whole story up from the early warning signal that something weird is happening, a precursor signal before the Navy came out and chased them. So that's the take-home message and the implications for this work. The technical term is that we're analyzing the multi-scale spatial behaviors of the system, and in doing so, we can actually detect but also predict illegal activities happening at sea. We're working, this is a project funded by NASA. It's a basic science research project, but we're actually seeing great utility in this work in an operational product. So we're working with Esri and having conversations with the Argentine Navy as well to operationalize these algorithms. What's next? Well, we focus on one place, the Patagonia Shelf, but we want to do this anywhere that there are these chronic illegal activity events. So narcotics trafficking in Central America, piracy in the North Indian Ocean, and in general, I'm quite interested in geopolitical risks in the South China Sea. I would mention this. My postdoc, John Woodall, and I, we have done other works in this area applying machine learning to mine oceanographic data for similar predictive analytics. And we've got a poster tomorrow morning at 9 if you want to come talk to us about that. The take-home message is this: with these kinds of technologies, we can detect and predict now illegal activities happening at sea, specifically illegal fishing, and this is a contribution to our global efforts to reduce these activities at sea and secure sustainable and healthy oceans going into the future. Thank you very much.
Also, we'd like to open questions from reporters in the audience.
Good morning, Boston Hunt, freelance. Question for Mr. Stowell?
Stowell, yeah.
Stowell, thanks. Are muons the only particles that are useful for this, or are there others maybe a little bit less useful, and could you maybe combine properties?
Yeah, thanks. So generally, the reason we use muons is because they're highly penetrating. So they're a lot heavier than an electron, which means they will punch through a lot more material. In cosmic ray showers, you actually get a whole mess of particles that come out. But a lot of those particles are actually absorbed even in the upper atmosphere, so they don't even make it to sea level. Generally, muons are the ones that you get for free that are heavy enough that they can punch through many meters of rock. Or that if you try to use other particles like electrons or gammas, they will get absorbed, and then you're also sensitive to problems where you can actually have sort of natural radiation from the rock around you, giving you sort of false signals that you have to watch out for. Whereas muons are highly penetrating, and also the way you detect them is they basically leave a nice straight line through your system, so they're a lot easier to select compared to those other backgrounds.
Harvey Leifert, freelance, also for Dr. Stowell. Can this be used horizontally also to find hidden or unknown tunnels? I'm thinking of the one from the movie where the Nazi train loaded with gold is hidden somewhere in Europe and nobody knows where, or anything like that.
Yeah, so there's been lots of work, even before the work we've shown, using muon tomography to look sideways through various objects. I think one of the most famous ones is looking for hidden chambers inside the pyramids of Giza. Basically, because it's cosmic ray radiation, these particles rain down from the upper atmosphere. So most of the muons that you see will be coming from directly above you. And as you go to higher and higher angles away from that vertical, so horizontal, you get much less muons. So you start to run into sort of time constraints in that you need to run for many months for the technique to work, to produce any sort of image. But it is possible, and it has been proven that you can do this sort of sideways imaging to look for those sorts of voids and things like that.
Jennifer Lehman, Popular Mechanics. This is for Dr. Watson. Hey.
Hi.
I was wondering if you could explain kind of like the relationship between the distance of these vessels. Like, are the vessels that are doing illegal practices, are they like further away from other ships? Like, could you kind of explain what that means?
Yeah, two answers to that. First off, I can't give you an accurate answer because we don't know the exact location of these illegal fishing vessels, right? They turn off their GPS transponders. But the assumption that we made to develop these algorithms was simply that I'm going to get away from the bad actor if I see it approaching, okay? Right? So if I don't know if John, my postdoc there, started like shouting down his phone at his friends or something like that, there you would all maybe move away from him, and that's the exact sort of thing that we went with in this analysis. For that Chinese fishing vessel, we assume you can't see it, but we assume that it's going to be repulsive, to want for a better word. It's going to push. People are going to get out of its way. And I mean, the trick is, there's more to this. The trick is, it's hard to distinguish. We really wanted to find a precursor signal, so the good actor is moving away from the bad actor as an early warning signal. But you would get the same response from spatial response of the good guys to a giant naval vessel steaming through them to chase the bad actors as well. So that's the next challenge for us, is to trying to pull out the precursor signal from the sizable perturbation that is the naval response.
Danielle Benton, KQED Science, also for James Watson. Are you combining this with other methods of trying to detect illegal fishing, such as detecting lights at night?
Yeah, so what's really nice about this technique, direct answer, yes. So we're working with NASA on their new black marble night lights data product, and NOAA's had a night lights product for a few years as well that we're looking to get data for too. What's nice about this is it contrasts with previous efforts to detect illegal activities, and those typically lean on contextual information, like the vessel ID, its history, where it's been. This is completely agnostic to that. If you just give me a map of where vessels are at a given time, whether it's from night lights or AIS or from radar, Esri have a new product coming out that focuses on just using radio transmissions, I believe. You can characterize its shape, and you can track the shape of the system as I've described through time. And so it actually requires minimal data to infer to throw the red flag that illegal activity is happening. I did allude to some other work that we're developing. So machine learning algorithms, very powerful in general, but extremely useful in this context. So in brief, the method that we've constructed, in addition to the one that I presented, takes satellite data on the biophysical characteristic of the oceans. So it's temperature, the currents, the wind speed at the surface, say, these kinds of things, and relates those things to patterns of fishing. And in doing so, we can predict if and when the ocean conditions are ripe for fishing to happen, and also illegal fishing to happen. And for the same study area, for the Patagonia Shelf, we have an accuracy that I was very impressed by, something between upwards of 80 to 85% accuracy for this machine learning algorithm. So John presented on that earlier in the week, but we'll also have some information about it in the poster. What we're trying to do is build a suite of tools that contribute predictive abilities. All the tools to date focus on detection, sort of retroactively. It's like forensics, which is very powerful, very useful, but prediction is more actionable for those who are trying to deter and to stop these illegal activities.
You have any other questions from reporters in the audience? Harvey?
Harvey Life at Freelance. This is for Melanie. I found your study fascinating, and I'm afraid my question is totally peripheral. I once crossed the Congo River between Kinshasa and Brazzaville, way up, and my recollection of that experience was millions of water hyacinths floating downstream. And I didn't see any in the lower basin there that you were showing. Where did they go?
Well, you know, that's very interesting because I know that area very well, and now there are no water hyacinths there. So I'm suspecting this was quite a while ago that you were there. And I don't know whether they've gone because of some eradication campaign or what it was, but there are no, water hyacinth is not a problem in Pumulebo anymore, which is the outflow of where the lower Congo plunges down from there. So, but presumably when they were there, they plunged down and they got completely chopped up by all those rapids and probably clogged up the sides of the river, but they've gone now.
More questions from folks in the room? Anyone on chat? No? All right, going once, going twice? And thank our panelists today.
Thank you all.
Thank you.
Thank you.
They'll probably be here for a few minutes if you come up with more questions. Otherwise, we resume at 11 a.m. with Osiris Rex.